The purpose of Lab 4 is to predict behavior of circuits containing resistors in series and parallel, use multimeters to measure potential differences in conventional current, and to study the behavior of capacitors and ohmic resistors. I'd like to note that the time dependence for RC circuits was experimentally determined to be 6.09 seconds. The main physics principle used in Lab 4 include the loop rule, which states the sum of all potential differences around a circuit loop equals 0, the node rule, which states the sum of currents flowing into a junction equals the sum of currents flowing out of a junction, impatience is equal to charge divided by voltage, and Ohm's law, which states the voltage equals current times resistance. We will use the Colorado PHET project construction kit program to model the circuits, including the series circuit. Series circuit is modeled with two 1.5 volt batteries, 2 ammeters, a 47 ohm resistor, and a 100 ohm resistor. Using Ohm's law in conjunction with the loop rule, the calculated theoretical current is found to be equal to 0.0204. This is experimentally confirmed by reading the ammeters in the circuit program, which all show 0.02 amps. Even if the ammeters are reversed, the current remains positive and with a reading of 0.02 amps. When the first ammeter is replaced with a voltmeter, the measured voltage is shown to be a value of 3 volts, with a subsequent ammeter in series reading a current of 0 amps. This occurs as a result of the circuit now being open and no longer closed. As a result, the voltmeter measures the potential difference of 3 volts from the battery. This occurs because the voltmeter has infinite internal resistance and therefore no current can flow through it. This is supported by the ammeter reading 0 amps of current. To calculate the potential difference around the entire circuit, the sum of all potential differences around the loop can be taken by segment. The loop rule states the sum of all potential differences around a circuit loop equals 0. This is supported by the sum of all potential differences shown in the chart equaling 0. The difference in potential are graphed and result in a potential difference of 0. The formula resistance equals the change in potential over current can be used to calculate the resistance of the resistors using the calculated current. This calculation results in a resistance of 47, 100, 0, and 0 ohms for the 47 ohm resistor, 100 ohm resistor wire, and ammeter respectively. Because the voltmeter has an infinite internal resistance, when it is used to measure the potential difference, it does not alter the ammeter reading. When a second ammeter is placed in parallel with the 100 ohm resistor, the reading on the ammeter increases to 0.06 amps, which is 0.04 amps higher than the ammeters read in series. This is supported by the node rule. Because the current splits in a parallel path, the resulting resistance is lower. This is further supported by the equation current is equal to voltage divided by resistance. The resistance decreases, the current increases. If the resistance increases, the current decreases. An RC circuit consisting of a 9-volt battery, a 10 and 20 ohm resistance light bulb, and a 200 millifarad capacitor is made. While the capacitor is changing, the light bulb is initially bright but then dims. The same observation is made when the battery is disconnected, causing the capacitor to discharge. The flux of current slows down with time in both scenarios. As a result of the battery being removed, the capacitor discharges and the direction of the current changes. The length of time the capacitor takes to charge and discharge is measured using a 10 and 20 ohm resistance light bulb. When the 10 ohm light bulb was used, the capacitor charged in 6.45 seconds and discharged in 9.39 seconds. When the 20 ohm light bulb was used, it took the capacitor 14.07 seconds to charge and 18.72 seconds to discharge. This supports the fact that the current travels slower through higher resistances. To determine the time dependence of a capacitor in a loop with a 30 ohm light bulb, the voltage of the capacitor for each second over a 20-second interval is recorded. As is shown by the first equation, the voltage difference decreases exponentially with time. Take the natural log of each side of the equation, graph the natural log of delta V over delta V naught. The slope of this graph will give negative 0.1641, which we can set equal to negative 1 over RC. From this, we can calculate the dependence constant to be around 6.09 seconds. In conclusion, the calculated time dependence constant was calculated to be 6.09 seconds. This is close to the expected value of 6 seconds with a percent error of 1.5%. In real life, the ammeter readings would have been lower than the true values as that resistance, which would affect the current reading. If the lab were done with a real battery and capacitor, the ideal model would predict the capacitor would charge instantly. So that's what the ideal model predicts. The actual charge time for the capacitor would be slightly longer than what was calculated in the simulated lab. This is a result of the real models having resistance within the circuit, which slows down the current and causes the capacitors to take longer to charge. Oh, stuttering. And I had to film in this box because I couldn't film without it being like this.